Before I begin my presentation, I have a question for you. How much kerosene can be saved in 1 year within a plane which is weight reduced by 1 kilogram, by only 1 kilogram? Any idea? So, through the weight reduction of 1 kilogram, there can be saved 3 tons of kerosene in 1 year. So over the whole lifespan of a plane, that's around 90 to 120,000 liters of kerosene. When we look at the rising kerosene prices and also at climate crisis, we see that we need to do something. And at NMB, Neue Materialien Bayreuth, we are developing a new titanium aluminide alloy, and we are manufacturing it by a completely new manufacturing process. But first, let's see, why titanium aluminides? We are using these materials in low pressure turbine blades, and here we have the density. I already mentioned we have a really low density in these materials compared to maybe nickel-based or iron-based materials, which are also used in low-pressure turbine blades. There are more advantages of this material. It has a high melting point, a high specific strength, and also high creep resistance and stiffness at really high temperatures. The left side, we see the phase diagram, and we see the 2 main phases, like the alpha 2 and the gamma phases. And we are working with a material with a phase composition at around 48% aluminium content. So I'm going to guide you through the presentation. First, I'm going to speak about the process itself. Then I'm going around the process optimization. And last, I'm going about the in situ alloying of the mentioned alloy. So first, we heard a lot about powder-based processes, and I think that's completely normal. We have like 40% of the sales in the complete additive manufacturing market that are going to powder-based processes. But today I want to speak about a wire-based process. And in wire-based processes, we have a few advantages over the powder-based process. We have nearly 100% consumption of the raw material. We also have high build-up rates, so that we can build large-scale parts in pretty short times. And when we look at the surface of the feedstock material, we have a lot less surface, so we are a lot less prone to contamination through oxide or other elements. And also the feedstock material, if we use standard wire, is pretty low priced. So what applications we have? We can do like, first I need to mention we can compare to maybe SLM, because we can do that complex parts. That's to say in the first range. But what can we do with this process? Here we see some examples we printed at Neue Materialien Bayreuth, for example a turbine blade. Yeah. And what it's also good for is for no longer deliverable parts. Here we see from Deutsche Bahn a part that couldn't be manufactured anymore with the old mold, so we can do it with the DED process. And also in architecture it's used for grid shell knots, like the architecture is getting more and more complex, so to combine these architectural parts we need some grid shell nodes, and that can be also processed by DED process. So now I'm going to tell you more about the process we have at Neue Materialien Bayreuth. First, we have a vacuum chamber, and we are working with a pre-vacuum. So that is enough to keep all the oxides out of the process. We also have 2 wire feeders, which are working with 1 pure aluminium wire and 1 pure titanium wire. And we have a wire preheating of these wires. It's inductive, so it's about a current. Yeah, and we have a carrier plate and also a heatable building plate, which arrived 2 months ago. And for the process, we have a 3-axis CNC platform. Like the maximum component size without heatable building plate, you see here, and we can heat the building plate up to 1000 degrees. So let's have a closer look at the process. You see it one time from up and one time from the side. We have a few advantages. So we can produce oxide-sensitive materials without having any oxides in the material. Also, through the vacuum, we can reduce the laser power needed, and we also can reduce the laser power by our inductive wire preheating. What's also possible with the two wires is the in situ alloying of new materials. And we hope, maybe we know a bit more at the end of the presentation, that we can have a reduction of cracks and residual stresses through the heated building plate. So let's talk about the process optimization. A lot of people think that DED processes are a lot easier to control than powder bed fusion process, for example. It is not like that, I can say. Maybe what's interesting, here are the most interesting parameters. And what is interesting, we have a wobbler, so we don't have to defocus our laser to get a bigger welding point. We can just wobble it around and so generate a much higher heating force and a big surface that we melt. We have the standard procedure. We first printed lines, then hatchings, then cubes, and then more complex geometries. So what is the normal formations in DED processes? We first have the drop formation. When there is too much energy in the process, the wire begins to form drops and drip on the surface plate. Then we have the soft transition with maybe optimal parameter set. And we have the sticking, when the wire is stubbing on the surface plate, when there is less power in the process. But that's not all. We have, through our 3-axis CNC machine, a direction-dependent process. So if we look at the different directions we are feeding the material, with front feeding we have a really high and narrow weld, and with the back feeding we have a flat and wide weld. So that's another complex thing we have to keep in mind. So if you look, we need a combination of different hatching strategies to reduce these geometrical inhomogeneities. So we did some hatchings, and first hatching was front and back feeding, alternating. So we see here we got a picture of the measurement, and here we got an optical measurement with a gum system. So here we see we have a pretty uneven layer geometry. In the middle it's pretty flat, on this one side it's pretty high. So that's because of the strong direction dependence of the process. And also we have a stubbing of the wire on the previous bed, because we are going there in 45-degree angle to the build plate and also with 90-degree angle between those two wires. So we did another hatching, and we did it with a complete side feeding. And here we see we have a lot more even layer geometry. We have a medium direction dependence, and we have no stubbing of the wire. So process. And lastly, we did a 45-degree hatching. So we see we have also even layer geometries, especially when we are alternating these two directions. We can get a really smooth and really even layer geometry. We also have nearly no direction dependence of the simple tracks, and we have no stubbing of the wire on the previous bed. So we decided for a hatch width of 2 millimeters and the 45-degree hatching. When we look at the whole process, beginning from the first layer to the last layer, we need to manage our energy input. Like in the first layers, we need to get a higher energy input to get the process rolling. But then we need to vary the laser power down to control the heat transmission from the bottom to the top. Like every layer, the bed is getting more hot, and so we have to regulate the laser power. Also, the wire heating is controlled. The wire heating is furthermore really important for the compensation of the melting point differences. So we have aluminium with around 660-degree melting point and titanium with 1,600 degrees. So we have a 1,000-degree difference between those two wires. Yeah, so this is a scale of development we did the last year. So here you see the cubes we built. And this is like our development over the last year. And up there you have the build-up rates. And to get it a bit more normal, or that you understand what this means, this part we printed in around half an hour. So I think it's pretty fast. Yeah, now we're going to talk about the in situ alloying of this alloy we're speaking about. I have to say, all the experiments we did here are without heatable building plate. So at the left we see the cube, and here the microstructure. It's pretty inhomogeneous, as we see. And here, for the people who like numbers, we have the process parameters. What's interesting to mention is that we work with an interlayer time of 60 seconds to control the cooling. So when we have a closer look, we have mainly these two structures. One is a dendritic one, and one is a lamellar one. And if we look at these EDX mappings, we can see that we have some parts with a high aluminium content and some parts with a less high aluminium content. And this refers to the gamma phase and the alpha 2 gamma phase, which is also proven by our XRD samples on the slide before, as you can see here. So let's have a closer look at the microstructure. We see we have these gamma phases there, we also have these alpha 2 gamma phases there, and we also have some blocky alpha 2. That's all normal, and with the heat treatment we can homogenize this microstructure. But what is not normal is this here. This is a complete titanium inclusion, so that means our titanium wire wasn't melted completely. So that is one thing we need to get more control of. So when we got our heatable building plate, we thought maybe that's going to change the thing. So here you can see the influence of our heatable building plate. This is the part without the heatable building plate. So we see we have a lot of cracks, even in the hatching patterns. And with the building plate at 650 degrees, we get rid of these cracks, even in the bigger scale. We also have a reduction of the residual stresses. You can imagine it's more like an annealing process if you slowly cool the structure down. So we get a reduction of these residual stresses, and we can process crack-free structures. One side effect is that we got a bit of homogenization of the microstructure, so we get a lot more lamellar structures in there. Yeah, to give you a summary and outlook what we did, and maybe two interesting values. The parts we printed have a porosity of less than 1%, so it's like completely dense. And we have an oxygen content of 0.02 weight percent oxygen. So if we compare it to normal titanium powder, we have like 3 to 5 times more oxygen in there when it's unfabricated. So yeah, it's pretty low, the oxygen content. What we realized was the in situ alloying of this titanium aluminide. We completed with a high build-up rate, and we manufactured crack-free components. The outlook is we need to further investigate the effects of the substrate heating, and we get to know the thermomechanical properties of these parts. So thank you for your attention, and I'm open for questions.
Thank you.